let's go here and talk about latent heat as I do my erasing here. Anybody remembers what latent heat was? You seem to know.
The amount of energy involved with the phase change?
That's correct. And so let's say we have a single component system such as pure water. What is the temperature change? During a latent heat, let's say vaporization, freezing. Let's say freezing. Yeah, pure water and freezing pure water. He already mentioned that the latent heat is the heat that goes with the phase change. Now I ask another question. What is the temperature change during that phase change? 0. And that's the fun thing. And actually, that's a tricky thing. Because if I tell you I have water at 0 degrees, I'm actually not telling you much. Do I have ice or do I have water? Liquid water. Right? So we start to work our brain into thinking some important subtleties. Right? So latent heat right, is the heat absorbed during a phase change. And so we're going to call this vaporization, evaporation, and ISF melting. The book has an H there. The way you are used to do your enthalpies with H. The problem is that H is also heat transfer coefficient, and I think the chances of reducing confusion is lower. Some of you might think this is the imaginary variable, but in that case, nothing I can do, right? So I'm staying also with the notation of the book, which I don't like, so that might change some. G stands for gas. S stands for solid. I don't know what F stands for. Maybe fluid, but the gas is a fluid too, right? So FG means you went to gas. SF means you went from solid to liquid, right? That's the notation. We can make a curve that you have already seen, and but it's so important. All these things I'm telling you are like the bedrock foundation of everything we're going to be doing. So this is T, temperature. This is so let's talk about water. Right? Let's start here at 20 degrees C. Let's say at 20 degrees C, we have a given enthalpy, whatever it is. Right? So as if I had a glass of water here. Probably the water in your bottle's over here. Okay. I increase the temperature now. What happens? Let's say I move up in temperature, move to the right on this axis. What happens? Curve goes up, right? Enthalpy goes up. Here is a blessing of God. Didn't have to be, but it goes pretty much straight. So the important concept of specific heat, there's a whole guy who rejects the concept of specific heat because says, what do I do with the derivative? But it is very important because it happens that this derivative is pretty much a constant value. It's not exactly constant. If you get the book I recommended, you're going to see that the specific heat for water or water vapor is tabulated every few degrees. And it's not exactly constant, but it's more or less constant. If it is more or less constant, we're going to call it constant. So good engineering is the art of the good lie. So you can never deal with reality. Reality is too much for our little brains. It's going to explode. But if we start to cut corners and say, this derivative, I'm going to say it's a constant. And I have good reasons to say it's a constant because it's more or less a constant. Now, mathematicians are just going to have an epileptic seizure and die, right? Physicists will want to kill you, and you will get the job done, right? So I have uploaded in the notes an example in how you would calculate enthalpy if the specific heat is not constant. Guess what? You do the integral. Doesn't change anything. But okay, so I keep increasing the temperature. Actually, I'm sorry for those of you who already started. I said 20 degrees. Let's make them here. So, I keep going up. So what's going to happen? Keep going. So what is the next thing that happens if I keep going up? At what temperature? Okay, at what temperature? 100 degrees? Anybody agrees something would happen at 100 degrees? But you're assuming something. And this is another part of engineering that is really important. I would agree with you. At 100 degrees, something happens. What happens? It starts to evaporate, right? It starts to turn into vapor, right? In saying this, you and I and all those who have agreed with us have assumed something. Atmospheric pressure, right? Which is what happens at sea level, right? But right, so this would be for 1 atmosphere. Absolute pressure. Good engineering, again, and this is actually part of your education to be engineers and design the things that can kill if they go wrong. So a good engineering means always assuming something and always being aware you have done it. Right? Okay, 100 degrees. What happens at this point? How does the curve keep going? Right, it's not going to increase the temperature, but it's going to increase the energy. Right, so actually what happens, we go up. This slope here, if this is 1, this is the CP of the, CP, I said I wasn't going to say that. Specific heat of the liquid, right? What is that height there? Say? Latent heat. All right? I keep going hotter. So now, right? And this would be the specific heat of the vapor at constant pressure, right? Because we're saying it's 1 atmosphere. All right. Let's put our glass of water in the freezer. Cools down, right? Out to where? Right? Because it's 1 atmosphere. Those of you chemists, you play all kind of games with funny pressures. In materials or mechanical engineering, we don't mess with those. But you do. So you better be aware of the things you do. Okay, what happens here as I keep cooling down with a curve? Goes down, right? And this would be the latent heat from going from solid to liquid. And then it keeps going down. And the enthalpy doesn't have a real 0, right? So, and here we would have 1 C S. This is quite important because now we can work the diagram in this other axis and say, okay, if I'm I were to have a system that is this combination of temperature and enthalpy, right? I can add heat to it. If I added this amount of heat that I marked in here, what do I know already? If I added this amount of heat, I know I'm melting things, right? So in chemical engineering, you typically talk more about like vaporization and things like those. But in material science, right? If I'm going to make a cast and I need to melt my iron, if I'm doing welding, for sure I need to melt my material, right? So I need to know what amount of heat I need to reach this amount of melting.